We know just 5% of the world. Really? So how could we know it's just 5%? 5% of what? Let's be honest, we know many things about the universe's material. We recognize baryonic matter, dark matter, and dark energy. Because of this knowledge, we can realize that the standard model matter is just 5% of the universe. If we want to talk about the universe, we should know what it is. So let's talk about these essential terms. Look at this cosmological equation of a state, where P is pressure and ρ is the energy density. By taking a derivative and making some adjustments, we will obtain this equation. So, the energy density ρ scales with A to the negative 3 times 1 plus W power. Matter refers to a fluid whose pressure is much smaller than its energy density, so it's a gas of non-relativistic particles. For matter, equation states parameter equals to 0, W equals to 0, so density varies inversely with A cubed. Can you see that? If the energy within a region is constant, the volume of region of space increases directly proportional to A cubed. Matter can be baryons, such as nuclei and electrons. Actually, electrons are leptons, but they are much lighter than nuclei, so we do not separate them. The other matter is dark matter. It's the most form of matter in the universe. There is an invisible halo of dark matter which holds galaxies together. The nature of dark matter is unknown. We usually think of it as new particles, but we do not know what it really is. Of course, some candidates exist, such as WIMPs, axions, machos, and primordial black holes. We use the term radiation to mention anything for which the pressure is 1/3 of energy density. So, if equation of state parameters equals 1/3, we conclude that energy density varies inversely with A to the 4. Now the dilution is not just expansion, but also redshifting of the energy of the particles. At early times, all particles of the standard model act as radiation. As the universe's temperature dropped, the masses of many particles become relevant and started to behave like matter. We call this light matter. Another particle is photon. They are massless and always relativistic. Photons and neutrinos were dominated energy density during the Big Bang nucleosynthesis. Maybe you ask, what are these neutrinos? Matter or radiation? For most of the universe's history, they behaved like radiation. But recently, they got small masses and become relevant. That makes them act like matter. The last particle is graviton. The early universes may have produced background of gravitons. The density of these gravitons is predicted to be very small, so they have a negligible effect on the universe's expansion. The last and maybe the most crucial role of the universe's expansion is cosmological constant. Matter and radiation are not enough to describe the universe's evolution, but the universe is dominated by a mysterious form of energy with negative pressure and hence constant energy density, which is called dark energy. But how can energy density be constant? A natural candidate is the energy associated with empty space itself. As the universe expands, more space is being created, and this energy increases in proportion to the volume. In quantum field theory, this calls vacuum energy. Unfortunately, quantum field theory predicts the size of vacuum energy much larger than inferred in cosmological observations. Observations also revived the concept of cosmological constant, which was introduced by Einstein. to make the universe static and unchanging in size because a gravitational model predicted it would collapse under its weight. After Hubble discovered the universe's expansion, the need for a cosmological constant faded, and Einstein called it his greatest blunder. However, this constant was revived later when astronomers found evidence that the universe's expansion was accelerating, something attributed to dark energy. The term dark energy is often used to describe a general fluid whose equation of state is not exactly that of a cosmological constant, or it may even vary in time. It's the failure of quantum field theory to explain the size of the observed vacuum energy that has led theorists consider more exotic possibilities. So we will typically use the term vacuum energy, cosmological constant, and dark energy interchangeably. Whatever it is, dark energy plays a key role in the standard cosmological model, the Landau-Sedien model. These are some of the most important terms when we talk about cosmology. In the next episode, I will discuss universe's history when matter, radiation, and dark energy dominated. So, stay with Universall and be curious.